Swayam Prabha. Digital India. Educated India.
So, good morning, and today we are going to look at a problem which has implications on our circulatory system. And as you all know, the heart pumps on a periodic basis, and that is essential for us to be alive and for the blood to circulate through the circulatory system. So, we are going to idealize this problem and try to understand some basics of this fluid flow problem by considering flow through a circular pipe, a circular tube under the influence of a periodically varying pressure gradient. So, flow in a tube. So, when I say pulsatile flow, I mean the pressure drop across the tube is varying periodically. So, you solve the problem where the pressure drop across the tube is constant, okay, and then you get the famous Hagen-Poiseuille equation and the laminar velocity profile. So, we are asking the question, what is going to happen if this pressure drop is going to vary periodically, as in the case of a heart beating for this and keeping the blood moving in the circulatory system. Okay. So, the problem is that of a circular tube, and you have a pressure gradient delta P, okay, and we are going to represent minus delta P as G0 times 1 plus epsilon sin omega t. What is G0? So, G0 is the pressure gradient, the negative dP dz. So, G0 is going to be positive, dP by dz is negative. So, the gradient of P is negative because I want the flow to be in the this direction. This is the z axis and this is the radial coordinate. So, we want the flow in the positive z direction. So, dP by dz is negative, and which means G naught is positive, okay. And this epsilon represents the amplitude of the periodic variation of the pressure drop, and omega represents the frequency of the periodic variation. So, this is the amplitude and this is the frequency of the periodic variation, okay. And what we want to do is we want to get some physical insights about this problem. So, the first thing is I want to model this thing like as a one dimensional flow problem, where I have only the z component of velocity present, okay. So, what this means is the governing equation is going to simplify to dou t equals minus dP by dz plus mu by r d by dr of r du by dr. So, what have I done? I am assuming my flow is axisymmetric, there is no theta variation. I am assuming that there is only radial variation present for the velocity, and this is a viscous term. This is a pressure gradient which drives the flow, and because we have time dependency, that is captured in the time derivative term. I am neglecting the convective terms, u dot del u terms, and I have neglected the derivatives, the viscous forces in the other directions, in the theta direction and the z direction. So, this is just to help us get some physical insight about what is happening. Of course, what you may want to do is solve this problem numerically using a software code, okay, and which may be more realistic, but you do not get the physical insights that we are going to get by doing the analysis that we are talking about. So, this I am going to again rewrite as okay. All I have done is substitute for the pressure gradient in terms of G0. Now, I want to talk about the heart is keeping on beating, and in this particular problem the velocity profile that I am interested in is the long term velocity profile as t goes to infinity. I am not interested in the transient. How does the velocity profile develop from t equal to 0 to t equal to infinity? So, we are focusing on the long term behavior of the system. Our focus is on the long term behavior of the flow as t tends to infinity, not on the evolution of the velocity from t equal to 0 to the final profile. I am not going to talk about steady state because the final profile is not going to be steady, it is going to be periodically varying because my pressure drop is varying periodically, okay. So, keep this in mind that we are only interested in the long term behavior. So, what this means is we really do not worry about initial conditions, because if you are interested in how it evolves from the initial condition to the final profile, then you are interested in the transient. We are not interested in that, we are only interested in the final state. So, initial conditions do not really play a part, okay. That is the mathematical implication of what I have just said. So, basically initial conditions do not play an important role in this analysis. The thing which I want you to understand, okay, is we need to solve this problem subject to boundary conditions. This is a second order equation. So, the boundary conditions are going to be use that at r equals r, the wall equal to 0, and use that at r equal to 0 is bounded, okay. And like I said, we do not worry about the initial condition, so I am not talking about the initial condition. If you want, you can put t equal to 0, use that as 0, the liquid is stationary. Now, what I would like to emphasize here is this equation is a linear equation. This is coming to the first order, this is also to the power 1. So, this are all, and this is a non-homogeneity, and there are two sources of non-homogeneity. One is this constant source 1 and the other is this periodic source sin omega t. So, because this equation is linear and the boundary conditions are linear, what I can do is I can use this principle of linearity and superposition and try to solve this problem considering only one non-homogeneity at a time, okay. So, equation is linear, there are two non-homogenities, I solve the problem using considering only one non-homogeneity at a time. So, what I am going to do is using linearity and superposition, we seek uz as uz 0 plus uz 1 times epsilon. This epsilon, so this basically, so uz 0 is the solution to now before I do this, what I like to do is I like to make this equation dimensionless, okay, and then we will use the principle of linearity and superposition. That is going to be more efficient to do. So how do I make this dimensionless? I need to have decide the scales. So the characteristic length scale is capital R, the size of the tube. Now I need to calculate what is the characteristic velocity scale. To get the velocity scale, since the flow is driven by the pressure gradient, I am going to balance the pressure force and the viscous force, okay. So if you look at it, there is a u here, and what I will get at the bottom and the denominator is a r squared. So I am going to define u characteristic as g0 times r squared divided by mu, okay. You can check and verify that this is indeed got units of velocity, and T characteristic I am going to define as r squared divided by nu. This is the kinematic viscosity. So this time T characteristic basically talks about what is the time taken for the momentum to diffuse over a distance r, okay. Now I want you to realize that there is another possible scale which I can choose for T characteristic, and that is the reciprocal of this frequency, okay. So there are usually several options available to you when you are making things dimensionless, okay. So another way to make it dimensionless is to choose T characteristic. We can also choose T characteristic as 1 by omega. So as we go along, you will see what are the advantages and disadvantages of choosing these two scales for T characteristic. Right now we will use this characteristic r squared by nu, okay, and we will make our equation dimensionless. So this equation talks about how the z component of velocity changes with r and t, and if I make it dimensionless, I have u characteristic is going to come out here dt star, u characteristic which comes out here is g times r squared by mu, and T characteristic comes out here from the denominator. So I get another r squared by nu divided by r squared, because T characteristic comes to the bottom, or let me do this in a better way. I am going to write this as rho times u characteristic T characteristic du z star by dt star equals g naught times 1 plus epsilon sin omega T characteristic times T star plus mu by r squared times d by d r star of r star d by dr star times u z star times u characteristic, okay. I am going to, all I have done is made this dimensionless by pulling out the characteristic values, and I can substitute now for the characteristic values, u characteristic by t characteristic, and what do I get? U characteristic is g r squared by mu, t characteristic is r squared by nu star sin omega TCH, omega is omega, TCH is r squared by nu. So, I am going to write this as nu times T star plus so, all I have done is substituted for u characteristic, and you find that all these coefficients will cancel off. There is a g here which cancels with g, I am going to get a g out here. So, at the end of the day, what happens is my simplified equation is in dimensionless form going to be du z star by dt star equals 1 plus epsilon sin r w t star plus 1 by r star d by dr star of r star du z star by dr star. This is my simplified dimensionless equation which I have, and this is subject to the boundary conditions u z star at r star equal to 1 is 0 and u z star is bounded at r star equal to 0. What I want to talk about a little bit here is this dimensionless term RW. This RW is a dimensionless parameter which is defined as omega r squared divided by nu. Okay. Now, what one can do is one can try to bring in a physical interpretation for this. This omega multiplied by r is some kind of a velocity, and r is a length scale, nu is the kinematic viscosity. So, you can think of this as similar to a Reynolds number. This is one possible interpretation. Another interpretation that you can have is RW is r squared divided by nu, the whole thing divided by 1 by omega. So, this is another interpretation for RW, the dimensionless number which arises. So, you see this particular problem is governed by only one dimensionless number RW, okay. There are no other dimensionless numbers showing up. Now, what is the numerator? This is the time scale for diffusion, and this is the time scale of the imposed oscillation, okay. So, this is another interpretation for the dimensionless number, and in the literature you may see people using this term called Strouhal number. So, whenever you have problems which have periodic forcing from outside, then the Strouhal number is used, which is the ratio of two time scales. The time scale of the momentum transfer like we have defined here, and the time scale of the imposed oscillation. Okay. So, that is what this is. Now, what we want to do is try to understand how does the system behave in the two limits of low let us say in the limit of low Strouhal number. So, if RW is low, how does the flow behave? Okay. If RW is low means the time scale for diffusion is low, it means it diffuses, the momentum diffusion is very fast and the imposed frequency is very slow. Okay. The time period 1 by omega is very high, 1 by omega is very high means the frequency is very low or the time period is very large. And you can look at the general problem of finite RW also. So, basically by doing a dimensionless analysis, we have reduced the problem to analyzing how does the system behave when only one dimensionless parameter is changing. Okay. So, if I can understand how the system behaves for different RW, I have fully understood the system behavior. And the other thing is, I talked about two different time scales, we will see the implications of that. So, this is the power of the dimensionless analysis, that the system behavior is captured by only one parameter, otherwise you would think it is captured by the frequency, it is captured by the kinematic viscosity, it is captured by the radius of the pipe, everything has been clubbed into one parameter here, the RW, the Strouhal number. Okay. Now, I am going to go and talk about the principle of linearity and superposition and say that we seek UZ star as UZ star 0 plus epsilon UZ star 1. Okay. So, how is UZ star defined and how is UZ star 1 defined? I am going to define it like this. So, UZ 0, UZ star 0 takes into account this non-homogeneity. UZ star 1, because there is already an epsilon here, UZ star 1 basically what I am doing is I am substituting this back here, okay, and equating powers of epsilon to the power 0 and epsilon to the power 1. Okay. How do I get these two equations? You can substitute this velocity form for UZ star here. So, you get UZ star 0 plus epsilon UZ star 1 and the epsilon to the power 1 is here. This is of order epsilon to the power 0. This equation is of order epsilon to the power 0. This equation is of order epsilon. What does that mean? I am substituting this here and collecting all the terms which are independent of epsilon, that gives me this term, this equation. I collect all the terms which are epsilon to the power 1, that gives me this equation. Okay. This is basically the principle of superposition. I am considering one non-homogeneity here and another non-homogeneity here. And both of these and since UZ star satisfies the no slip condition, each of this must satisfy the no slip condition. UZ star is bounded, so each of this must be bounded at r equal to 0. Okay. The boundary conditions are u z star 0 equals u z star 1 equals 0 at r star equal to 1, and u z star 0 equals u z star or comma u z star 1 is bounded at r star equal to 0. Now, as far as u z star 0 is concerned, this is the velocity field that you are going to see when the pressure gradient is constant 1. Okay? And so, when the pressure gradient is constant, in the long term I am expecting the velocity field to be steady, and so what I can do is I can neglect the time derivative term here. So, at order epsilon to the power 0, velocity field is steady, and therefore time derivative can be put equal to 0. Why is the velocity field steady? Because the pressure gradient is constant. So, I am expecting velocity field to be steady, and then you can solve subject to the boundary conditions of no slip, and you will, what is this? You are going to get your laminar flow velocity profile. Okay. So, this will give me u z star of 0 as 1 by 4 multiplied by 1 minus r star squared. This is the parabolic laminar profile. Okay. So, this is what you expect, because at order epsilon to the power 0 my pressure drop is constant, I will get my laminar velocity profile. So, what we want to do now is, so we have this base profile, and because of the periodic oscillations, the periodicity is going to be on top of this base profile. So, I have velocity field, on top of this it gets modified by this periodic fluctuation, and I get an oscillatory velocity profile. Okay. And how do I get that? By solving this problem at order epsilon to the power 1. So, this is my velocity profile in the absence of any periodic variation, and so u z star 0 is the velocity in the absence of periodic variation. U z star 1 is the correction to u z star 0 because of the periodic variation of delta p. Okay. What I want to do is, I want to first talk about the case where Rw is very much less than 1. So, very, very small. In fact, Rw is tending to 0. Okay. So, now if I put Rw 0 here in this problem, okay, what do I get? I will get u z star of 1 is defined by a flow where there is no pressure gradient, and that is something clearly incorrect, something is wrong, because I want to include the effect of the pressure gradient. Okay. Here this means sin RWT goes to 0 and UZ star of 1 is defined by no delta P. And what we wanted to do is we wanted to understand how does the flow behave when there is a pressure gradient which is varying periodically in time with small omega. Okay. So, this gives you some clue that our scaling has to be done in a different way. Okay. So, supposing you had done the scaling in a different way, then maybe this problem would not have arisen. So, what I am going to do now is I am going to define T tilde as R W T star. See, this is also dimensionless, dimensionless is also dimensionless. Only thing is this is a new time scale which is R W times T star. And now what is going to happen is I am going to replace this T star by T tilde, and this is not going to get modified because there is no T here. Okay. So, if you want to substitute this thing, so dt star RW equals to dt tilde. So, I am going to write dt star as dt tilde divided by RW. So, this equation now becomes RW du z star of 1 by dt tilde equals sin T tilde plus 1 by R star d by dr star of R star du z star 1 by dr star. Okay. So, what I have done, I have just rescaled this time. Now, by doing this rescaling, the RW is coming with my time derivative. This term does not have RW anymore, this is my periodicity is retained, and I have the viscous term. So, again in this formulation with this new definition of dimensionless parameters, I can now in this equation look for the solution in the limit of RW going to 0. As if RW goes to 0, that means I can basically neglect this term. I am still able to capture the effect of the periodic variation of pressure and the modified velocity field. I have a modified velocity field, the periodic pressure, but now all I am saying is the time derivative is not important because RW is very small. Okay. I want to here talk about the fact that if in our problem we had used 1 by omega as TCH to begin with, we would have gotten this formulation. Okay. We would have gotten this equation if TCH is chosen as 1 by omega, because you can see if TCH is chosen as 1 by omega, I will get T tilde here. Okay. Okay. So, now if RW is very much less than 1, I can approximate this as sin T tilde plus 1 by R star d by dr star of R star du z star 1 by dr star. So, what I am going to do is I am going to seek u z star of 1 as f of R star times sin of T tilde. Remember, this uz is a function of R and T, and I am looking for uz as a function of R star and sin T star because this is sin T. I can substitute this expression back here. This is derivative with respect to R, and only this is going to contribute to the derivative. Sin T star is going to stick outside. Okay. If I substitute this here, f satisfies 0 equals 1 plus 1 by r d by dr of r df by dr r star. Okay. What are the boundary conditions I have to solve this subject to? F at r star equal to 1 is 0 and f at r star equal to 0 is bounded. So, basically what this means is, in the limit of r w very much less than 1, my velocity is going to be of this, can be of this form. It is of this form because it satisfies this differential equation, sin t cancels off. And what this physically means is, in this limit of r w very much less than 1, the pressure drop is varying sinusoidally, the velocity is also varying sinusoidally, and so the velocity and pressure drop are in phase with each other. Okay. So, in the case where r w is very much less than 1, velocity and delta p are in phase. So, basically this is a limit where omega is very small, is r square omega by nu, okay, and so the pressure drop is varying very, very slowly, and momentum diffusivity is very, very fast. The time scale for diffusion, momentum diffusion is very, very fast, or very, so the t is very small, the time scale, the numerator is very small, r squared by nu, t is very small, and therefore the momentum diffusivity is able to catch up with the delta p and the velocity is in phase. So, if my pressure drop is varying slowly, at every instant of time my velocity adjusts to the new pressure drop, and therefore the velocity and delta p are in phase. Okay. And that is a very important conclusion we have. Now, this particular equation can be solved because it's a simple ordinary differential equation, and I will solve that now. Df by dr star equals minus 1. Integrate this once, I will get r star df by dr star equals minus r star squared by 2 plus C1. Bring this r star below, you get df by dr star equals minus r star by 2 plus C1 by r star. Integrate this one more time, you get f equals minus r star squared by 4 plus C1 log r plus C2. This is the f. Now, because the velocity is bounded at r equal to 0, this goes to 0, and you can use the other boundary condition and calculate what is C2. Okay. So, f can be found out. If f can be found out, then u z star 1 can be found out, because u z star 1 is just f multiplied by sin of t. So, this way we have found what is the modification in the parabolic velocity profile because of the imposed pressure drop, which is varying periodically in time. Okay. And the important point is that the velocity in the limit of r w being very small, velocity is in phase with the delta p. We want to analyze the case if general r w, I mean not very small r w. So, now the equation will be the same. T star plus okay. This is the general equation for general R w, when we had very low RW, I neglected this. Now I cannot neglect this because RW is not very small. Now supposing I want to solve this equation, can I use the same approach as before? That is, can is use the star of 1 of the form, let us say some h of r multiplied by sin t star, because this is what I did. I am assuming for general RW my velocity is in sync with my pressure drop. Okay. So, I am going to substitute this back inside here and see what I get. When I substitute this back inside here, I get RW cosine t star derivative with respect to t star times h of r equals sin t star plus 1 by r star d by dr star of r star dh by dr star times sin t star. Okay. I am just substituted for uz this h multiplied by sin t star. What you see is I have sine here, I have sine here, but I have a cosine here. So, basically I cannot cancel off the sine and get an ordinary differential equation in h. Okay. And if I had gotten an ordinary differential equation h, then I could have solved for it, because then again velocity will be in phase with pressure drop. But here I have cosine, I have sine, I have sine. So, basically this gives you a clue that for general RW the velocity will not be in phase with the pressure gradient, the pressure drop. Okay. So, basically here, since sin t star does not cancel, velocity is not in phase with delta p. Okay. What do I mean? So, delta p, let us say, is varying periodically like this, and velocity is, I need to draw this thing in a better way, but velocity is also in phase. I am just drawing, this is not 0. Okay. This is, let us say, delta p, and this is uz. The maxima and minima of delta p and uz coincide. This maxima and this maxima, this minima, they coincide, and this means delta p and uz are in phase. And this is the situation for RW very much less than 1. For general RW like this, the thing may be shifted. Delta p and uz, the maxima of delta p and uz star of 1 do not coincide. Therefore, delta p and uz star of 1 are not in phase. Okay. So, in phase means delta p is going as sine, velocity is also going in terms of sine. The amplitude may be different, but they are going hand in hand. Maxima of delta p, maxima of u are same. Maxima of minima of delta p, minima of u are occurring at the same time. That is what I mean by in phase, and that is only in the case of low frequency, when omega is very low, when RW is very low, the Strouhal number is very low, the way I have defined it. Momentum diffusion is very fast. Okay. So, as soon as delta p changes periodically from one value to the other value, it is changing so slowly, my momentum diffuses so fast that the liquid quickly adjusts to this different pressure drop. So, I have delta P1, I have delta P2, next time instant the liquid quickly adjusts to the new pressure drop. Again you change it, liquid quickly adjusts because the frequency is very, very small. If the frequency is very fast, the liquid will not be able to adjust and there will be a phase lag, and that is what you are seeing. So, this kind of insight is what you get when you do this kind of analysis. I mean, if you directly went to one of the software codes programs and ran the simulation, you would not be able to get this kind of insight. You may get results, but you may not get insight. So, that is one thing. How do you solve this problem for general RW? I will give you a clue. The problem is coming because sin t on differentiation gave me a cosine t. So, one way to overcome this problem is if this is written in terms of an exponential function, because exponential function on differentiating gives me the same exponential function. And if you remember, we can write e power I t as cos t plus I sin t. So, you can basically convert this non-homogeneity to sin t star can be written as the real part of e power I t star, or is the imaginary part. Sin t is the imaginary part of e power I t star, right. So, what I could do is I could solve this problem with e power I t star as my non-homogeneity. It is a complex number. I find the solution, I take the imaginary part of the solution, and that will give me the solution which is of interest to me. Okay. So, we can use this, solve So, I have just changed the non-homogeneity to this. So, I can solve this problem because now we can write u z star of 1 as some h of r multiplied by e power I t star, because when I differentiate e power I t star, I will get by e power I t star, I will get an I. I will have e power I t star and I can cancel e power I t star, I get an ODE in R and I can solve, and after I find the solution I take the imaginary part of the solution. So, this is the way to do it, but if you understand the general concept then you can employ. Thank you.